3D printing in medicine. Module 6. Lesson 1. Post-processing techniques for 3D printed components. Introduction, Beyond Printing. In Module 5, we learned how segmentation transforms imaging data into 3D models tailored for specific medical applications. Once these models are 3D printed, they often require post-processing to meet functional, aesthetic, and regulatory standards. Post-processing ensures the final product performs as intended, whether it's a surgical guide, implant, or educational model. This lesson delves into post-processing techniques for 3D printed components, focusing on surface finishing, coating applications, heat treatments, and sterilization methods. By mastering these techniques, learners can elevate the quality and usability of their 3D printed parts for both medical and industrial applications. 1. The importance of post-processing. Post-processing refers to any steps taken after 3D printing to enhance a part's properties, functionality, or appearance. It is critical for achieving surface improvement, eliminating layer lines and imperfections to reduce friction or wear. Mechanical strength, enhancing material properties through techniques like annealing. Biocompatibility, ensuring medical parts are safe for human use. Aesthetic appeal, refining the part's finish through polishing or painting. For example, a surgical guide printed using resin may require UV curing to solidify the material fully and sanding to ensure smooth edges. 2. Surface finishing techniques. Surface finishing improves the texture and visual quality of 3D printed parts. Sanding. Purpose, removes visible layer lines and smooths rough surfaces. Method, abrasive materials, such as sandpaper, are applied manually or with machines. Applications, commonly used for plastics like PLA or ABS. Polishing. Purpose, refines the surface further to achieve a glossy finish. Example, resin-based models polished after sanding for a mirror-like appearance. Chemical smoothing. Purpose, dissolves surface layers using solvents for a smoother texture. Example, acetone vapor smoothing for ABS parts creates a polished, seamless finish. 3. Coating applications. Coatings enhance durability, aesthetics, and functionality. Painting. Purpose, adds color, protects the surface, and improves weather resistance. Applications, common for decorative or outdoor use parts. Powder coating. Process, applies a dry powder cured under heat to form a tough protective layer. Advantages, offers resistance to corrosion, scratches, and wear. Ceramic coating. Purpose, provides heat resistance and a hard surface. Applications, used in parts exposed to high temperatures, such as dental or engineering tools. 4. Heat treatments. Heat treatments improve the mechanical properties of parts. Annealing. Process, slowly heating and cooling a part to relieve internal stresses. Applications, enhances durability and dimensional stability in plastics and metals. Hot isostatic pressing, HIP. Process, combines high pressure and heat to eliminate voids and increase density. Applications, frequently used for metal parts in aerospace and biomedical fields. 5. Sterilization methods. Sterilization ensures medical components are safe for human use. Autoclaving. Method, uses high-pressure steam at temperatures above 120 degrees Celsius to eliminate contaminants. Limitations, not suitable for heat-sensitive materials like PLA or certain resins. Gamma radiation. Method, uses high-energy gamma rays to sterilize parts without heat. Advantages: ideal for intricate or heat-sensitive geometries. Ethylene oxide, ETO, sterilization. Method: employs a chemical gas that penetrates complex structures at low temperatures. Applications: common for intricate medical devices or assemblies. 6. Support removal. Many 3D printing processes require supports, which must be removed post-printing. Manual removal involves breaking off supports, often followed by sanding or polishing to smooth surfaces. Dissolvable supports uses materials that dissolve in specific solvents, leaving a clean surface with minimal effort. 7. Post-processing for specific materials. Post-processing needs vary depending on the material. Plastics. Sanding, chemical smoothing, and painting are common. Example: PLA part sanded and painted for educational models. Metals. Machining, polishing, and HIP treatments improve strength and surface quality. Example: titanium implants undergo polishing and heat treatment. Resins. UV curing solidifies the material fully, while sanding and painting refine its finish. Post-processing transforms raw 3D prints into functional, aesthetically refined, and application-ready components. By selecting the appropriate techniques for the material and intended use, professionals can enhance the quality and performance of their 3D printed parts. In the next lesson, we will explore the certification and regulatory requirements for 3D printed components in biomedical applications.